talk?
Yeah, and I'm going to be doing it on this questions computer, if that's okay. So just a second, let me pull it up. All right, and then let me make sure I'm sharing my screen. Can everybody see this?
Yes.
All right, cool.
Thank you.
All right. My name is Alan, and my co-author Sanjay Basu is also here in person, and I'm presenting Most Language Models Can Be Poets Too, an AI writing assistant and constrained text generation studio. This is a system demonstration paper. Language models today are really great at generating text, but not with hard constraints. The majority of constrained text generation research right now looks at soft constraints, such as trying to generate text where a particular word appears somewhere in a sentence, or even something like trying to generate text that's happy. But I care about a different kind of constraints, which are the kind that maybe poets or creative writers have been using for a while, which is generating something with a certain number of syllables, or generating what are called lipograms, which are works that systemically omit a particular character, such as the letter E. Beyond that, language models are really bad at following these kind of constraints. There was some work from, I believe it's an individual named Gwern, that showed that when you fine-tune GPT-2 on a haiku data set, it's only generating the correct kind of 575 syllable format about 60% of the time. And even Scott Alexander notes that, GPT-2 and other language models don't appreciate rhyme and meter. But we show that it's really not difficult to simply modify how we decode, and therefore to get language models to generate text in a way that follows the constraints given 100% of the time. And there are a whole lot of different kinds of constrained writing beyond lipograms. So for instance, maybe you want to generate something where the lengths of each word are the number pi, or you want to generate something from a restricted subset of English where you ban all forms of the verb to be. You might find that some of your English teachers have encouraged you to write in this E prime style, as it's supposedly a little bit more like descriptive, right? So, and there's far more beyond this. All forms of poetry come up here as well. So the goal of this paper is to show that we can generate things that don't violate the constraints. We want to examine, at least from a cursory standpoint, what happens when this is the case. And then we want to explore kind of other potential usages for this technique beyond creative writing. I talk a little bit about the potential for this to be applied in an adversarial context in the end section. So we contribute the following innovations. So the first thing is the general technique. I didn't actually use this term in the paper, but I would call it filter assisted decoding. And it's really simple. Just go through the entire vocabulary before the decoding step of your language model, and then check, does the particular word or subword violate the constraints that we have? If it does, throw it out and then decode as normally. So the second innovation we add is a GUI Python desktop app called Constrained Text Generation Studio. And this is really the thing that's aimed at the creative writing community. The third thing we introduce is a Hugging Face space named Gadsby. This is not related to the book The Great Gatsby, but related to the most famous lipogrammic text called Gadsby here, which is a 50,000 letter or word novel that doesn't use the letter E, written in 1939. It's also famous as a rare book, and original copies of it will go for about $4,000 to $7,000. This Hugging Face web app also has an additional functionality that I ended up writing about a week before this presentation, when I realized that this technique also works on text-to-text models. So I also got it to work on constrained summarization, constrained translation, all other sequence tasks. So this is to show that this technique is universally applicable. If your language model exposes its entire probability distribution, you can use this. That means everything except GPT-3, which is paywalled and doesn't give the whole distribution. So that's that. And then we also introduced 2 data sets for evaluation. I only mentioned one of them in the paper because the other one came recently. The one that we do analysis on is called Lipogram E, which are the 3 English books I could find freely available that don't use the letter E, as well as the one book that I could find that follows this 1-syllable constraint, which is Robert Caro's, I'm sorry if I'm mispronouncing the name, in 1 syllable. There are other books that claim to be 1 syllable, but they cheat, and so they were not really suitable for this data set. So let's talk about the filter-assisted decoding. So, we can do it trivially for some constraints, even on subword tokenized models, right? So banning a particular letter will not cause any problems with your decoding of subwords, can be decoded as normally, and you don't ruin your model to a certain amount. But if you're trying to, for instance, count syllables, which is something that's going to require kind of a surrogate model or surrogate technique, it's not going to, basically at every moment, the model will sometimes generate a full word and sometimes generate subwords or even punctuation or spaces. And when that technique, or when subwords are being generated, then this technique is worse because it systemically omits all of the subwords. But don't fear, there are large-scale language models that have fully word tokenized vocabularies and significantly larger vocabularies, because this is a technique where we want more words. So Transformer XL came out, which is kind of I believe it's an autoregressive model that has some kind of benefits about supporting long sequence lengths. But the problem is that it's actually a lot slower to decode from and takes a lot more memory. And then I also mentioned in the paper that if we can get subword tokenizers that can basically signpost, as in tell us, hey, I'm generating a subword and not a full word, then we can write a little bit more logic and then get our technique working on all subword tokenized models as well, with all constraints and not having this problem I mentioned. So we find that some filters eliminate more words than others. So for instance, banning the letter E removes about 30% of the vocabulary, and therefore, you can imagine that that's going to impact your model a lot. But others, such as E prime, it's only about 100 words, and therefore your language model is not significantly impacted. The more of high probability words that are systemically omitted, the more likely your model is to be naughty. And when I say naughty, I mean like really naughty. For instance, if you do a lot of constraints. So while I was writing this and using this tool, I've observed all sorts of problems: gibberish, repetitive loops, computer code. And the personalized information is actually something that I talk about a little later in the context of adversarial potential for this method. So let's talk about Constrained Text Generation Studio. It's an AI writing assistant. It was written using the DearPy GUI library, which is an excellent GPU accelerated library. I even have tiling enabled there. So if you're familiar with tiling window managers, you'll find that you can kind of tile around the little UI elements. So a fun little thing. It's built using Hugging Face. They're kind of the best model store right now, so you can take any model and just put the name of the model and then it'll download it and then use that technique. It supports 21 different constraints, and you can enable any combination of them at the same time. We also have some text transforms that allow you to normalize your vocabulary before the decoding step, which kind of helps in some cases, since language models frequently don't have extreme, some of these constraints can require some transformation beforehand. So the available constraints, I have a whole list of them. I'm only going to talk about the interesting ones. These are all syntactic, kind of where characters are constraints. Then we have things such as string edit distance matching, where you can use any kind of distance metric here. We have things like phonetic matching, where we use the double metaphone algorithm from the phonetics community to phonetically match. We can do semantic matching by taking a fast text model. We can take a particular word we want to be semantically similar to, and then a particular cutoff on the cosine similarity between this word and all other words in the vocabulary. And then we can count syllables using the pronouncing library, and same with generating strings that match a certain stress pattern in meter as well, also using the same pronouncing library. The big one for poetry generation is probably rhyme, hence most language models can be poets. It really comes from this one. And then I show a few other techniques like palindromes. These are word level palindromes, unfortunately, and things like anagrams and isograms. So this is a screenshot of what it looks like. I apologize for kind of some of the problems with viewing the text, but on the left text box is where you would type yourself, and then you have some buttons here that you can click to have the model predict a certain or generate a certain number of tokens, and then you can enable whichever filters you're interested in, and then right click in that text box and see a list of continuations, such as up here. In this example, the constraint is banning the letter E and forcing the letter A, and I apologize if it's hard to read, but the most likely continuations here, like that and what and are extremely unlikely. So we see that even these two constraints are already probably banning more than 50% of the vocabulary. So the second thing, the Hugging Face web app, Gadsby, this is accessible to anybody, and you can play with it yourself. So I show taking GPT-2 medium and then having it generate from a prompt of I do, where we ban the letter E, and then getting a kind of standard GPT-2, somewhat gibberish, not gibberish. I mean, it's like good text, but it's certainly not as high quality as something like GPT-3, but it's still very good and proves that this technique works. And then I also show that we can do the text to text. So this is a Pegasus CNN Daily Mail summarization model. And then we summarize a document about the Eiffel Tower. And we see that abstractive summarization models already have this problem of hallucination, right? So in the generated sequence, it tells us two different heights, says that the Eiffel Tower is two different heights. One of those is not in the source text. The technique I'm describing probably increases the risk of hallucinations from these models. The data sets we introduce are Lipogram E, which are 3 books, Gadsby, as you've already seen, A Void, which is a much more modern one. I think that came out 2008. And then a book called Anoia, which is actually a work where each chapter only uses one vowel. So of course we have to omit the chapter that uses the E vowel only because that violates the constraint, but that's not actually very much of it. And then we could computationally go through existing large scale data sets and try to extract sentences or paragraphs where the language model is, or sorry, where the sentences don't use the letter E. This actually comes up reasonably often. However, we wouldn't have coherent narratives. The data, maybe it would jump around topics all the time. And I just think it's more interesting to study, works where there was an intention to have this constraint. And then I think I already talked a little bit about the 1-syllable data set. And then the only problem with that is that proper names are not, that they don't change the names of people to make it 1 syllable. So that's the one thing you'll have to do if you're really trying to guarantee the constraint is remove proper names. And so I do an experiment. The experiment is mainly to show that we can eliminate constraint errors, right, which are pretty natural. So we study this on Lipogram E. I choose GPT-2 because it's really easy to fine tune. And the main thing I show is that this technique with the constraint filter always improves perplexity on this data set for an obvious reason. We've banned errors, right? So anytime it would generate something with the letter E, that's obviously wrong. So by doing this, we get first, when we haven't fine-tuned the model, a pretty decent improvement on perplexity and absolutely all constraints followed. And then once we fine tune on this data set, we find that the perplexity drops significantly less just because the model has learned mostly to ignore the letter E, but not completely. And so some future work ideas are kind of trying to extend this towards DALL-E or stable diffusion, which would be interesting if we could do like a pixel-based technique where we say, hey, you can only generate from certain pixel subspaces. I've actually looked into this and I would love to do that work, but I'm just not a computer vision expert. So it would also be really cool if we could test this on massive models. We could test it on Bloom once anybody can get fast inference working on it, but GPT-3, the paywall. And then finally, if you want to get a language model to leak information that you're searching for in an adversarial context, if you know what you don't want or like what isn't in that personal information, you're whittling away at the states or at the latent space that you're sampling from where you're trying to search for this. So this could take, a task that would require 100,000 generations and reduce it by potentially an order of magnitude. So that's it for here, and I really encourage you all to go test out the Gatsby demo, and all code and data sets are available on GitHub as well as on Hugging Face to make it easy to consume. So yeah, I'm now open for questions.
Thank you, Alan. It's a really nice talk. So can you hear me?
Thank you so much, Aaron, for your great presentation.
Yeah.
Yeah.
Okay.
Any questions or comments?
Okay. Can I ask a question, Colin?
Yeah.
Okay. Thank you, Alan. So basically, it is fantastic.
Yes.
This is really fantastic. So basically, I'm just interested in several things. The one is that, so how about the inference speed when we apply our current model to the real world application? I mean, the how fast is it for online usage?
Oh, okay. So person who is really, really good at programming can,
Okay.
it shouldn't, because what you're doing basically is you decode the whole probability, like all of distribution, and then you run a filter function. So it depends on how well you've coded the basically, look through each word and then decide return true, return false. I wrote this to be research code, so some of them do slow down the decoding significantly, but I'm not really an expert on the whole, fast writing this stuff to be super fast. So I claim that this technique, when applied by somebody who's more of an expert on that kind of programming, should be really fast and should not really impact. But again, depends, like when you're using surrogate models, like the fast text model, that will slow things down significantly because of the cosine similarity calculations. So, yeah.
Okay, thank you, Adam. Thank you very much.
Thank you. Any other questions or comments?
Hello.
Hi.
Yeah, we can hear you.
Oh, yes. I have a thanks for your presentation, and I have a question about the data sets. I say lipogram E data sets, right?
Yeah.
Why you choose the letter E? Yeah.
So it is, there are a few other lipogrammic works. I found one that I think omits the letter A. The main reason is that this is the most common constraint in kind of this constrained writing community. And beyond that, there's actually like people who play the game of trying to write without the letter E. There's a subreddit called Avoid 5 because they don't want to say the fifth glyph, which is the letter E. And so they call it Avoid 5. It's got like 30,000 subs on Reddit. And so folks like that are kind of generating more lipogrammic kind of text in the wild. And maybe in the future, another data set could be created from that subreddit that isn't like this prose narrative, still follows the constraint. The other reason I just choose lipograms in general is you can control F into the data set and look for the letter E and verify trivially that it's not there. So that's the main reason, is that we won't have any kind of errors, like for instance, with one syllable where the syllable counting algorithm may make mistakes once in a while, right? So that's why I do the analysis on lipogram.
Okay. It's interesting. Yeah. Thank you.
Thank you. Any other questions?
Yeah.
So how common is the constraint? Because as you said, it is a letter E because it's
Yes.
we use the letter E because it's easier to detect.
Yeah.
So how complex can those be, like the constraint?
Yeah. If you didn't hear, she's asking how complex the constraints can be. I don't believe there's any limit, right? So if you look on here where it's enter the list of strings that you don't want in each word, I could put, the letter A in there as well and have it ban both. And then I could put words in there too, and it would look for that substring everywhere. So I've tried to be extremely flexible and make it where there's kind of no problems there. And then the constrained text generation studio has the additional ability of you can enable any combination, whereas in this demo, you can only have one at a time. So I believe it should be as complex as you want it to be, is what I would say.
Sorry, maybe a follow-up question.
Sure.
Does it have to be literal then? Like what you want to keep it out, does it have to be literal? Or is there some kind of, I'm just wondering, for privacy preserving, for example. So maybe I don't really know what I'm expecting. I know it's a name, and I don't want any name. So is it also possible to somehow use this kind of more abstract, or you need to format it?
I think to answer your question that yes, you could use it for more abstract rules in principle. I don't think I've written a filter in that exact style, and I'd have to understand more. But the general idea of writing filtering before decoding is, I think, a kind of a universally applicable. This is plug and play. That's a big value add, I think, of this method. Yeah.
So I'm wondering if this application can be applied to non-English language models.
Yes, indeed. And in fact, if you go on the text-to-text one, I actually made a bunch of LinkedIn posts like showing kind of some of the examples of like French to English, English to German. And then the problem is I don't really speak these languages, so I was posting them to the community with the hope that somebody would be able to know. But like an example is there's some kind of like thing in Spanish where it's like something about a glass of water. It's like an idiom. And then when it translates water into English, it uses aqua instead of water. So I think that this technique is actually really neat when it's applied to translation models, and that could be a very active place for future work. All right, I think that's it for questions. All right, thank you guys. It was a pleasure.
Thanks for all of the questions. Next talks. Yeah. Thank you very much. Yeah.
Allow me to
Very
introduce
fantastic.
next paper, and thanks for Oracle's cool work. It's
Application.
really interesting.
Yeah. So the next, yeah.
Oh, okay. Let's introduce next paper from Hanyang University, Republic of Korea, and the paper's name is Insurance Question Answering for Single Turn Dialogue Modeling. Let's welcome.
Yes, thank you.